Hello everybody. Um, we're going to start learning module 2. In this learning module, we're going to simulate the flow inside a pipe. More specifically, we're going to study and simulate laminar fully developed flow in pipes. So in this learning module, a thermally and hydrodynamically fully developed laminar flow in a pipe will be simulated using ANSYS Fluent. Consider a pipe flow as shown in this schematic. The flow with an average velocity of 1 meters per second and a temperature of 300 Kelvin enters a pipe with a diameter of zero point 0.2 meters and a length of 3 meters. So note that the length of the tube has been chosen so that with the condition that we have for the flow, the fully developed condition is achieved at the end of the tube. So a constant heat flux of 250 watts per meter squared is applied to the flow from the tube wall. So a constant and uniform heat flux is applied. If you remember from your heat transfer course, we know that in this condition, the Nusselt number is going to be a constant value. More specifically, it's in the order of 4.3. So the exit of the pipe is exposed to atmospheric condition. The simulation will be performed to obtain the velocity profile at the exit. So we want to know if we can get the parabolic velocity profile that we expect to see in fully developed condition. And we also will be looking at the Nusselt number at the middle and at the end of the pipe. And as I said, we know that Nusselt number in a pipe flow for a laminar and fully developed condition is a constant number, so we do not expect the Nusselt number to change from the middle section to the end section. The velocity profile and Nusselt number, as I said, will be compared with available analytical solutions towards the end of this video. The flowing fluid has the following thermophysical properties. These properties may not represent a specific fluid, but it's been chosen so that the fully developed condition is met. But you can still do the same computation for any fluid that you may have. So, important thing that I want to emphasize is that, as you see, this is an axisymmetric flow condition. So instead of working with a 3D geometry, the software allows us to work with a 2D geometry, which is shown here in orange color. The computational domain that we're gonna consider is not a 3D model, is actually a 2D axisymmetric cross section of this flow, and we will see how the results will be. Okay, let's start. I'm going to execute Workbench as before. It will take some time to initialize. So once I am in the Workbench environment, I can drag Fluid Flow Fluent and drop it here in the project schematic section. Then I can proceed with saving this project. I know exactly where I want to save this, so I can copy the address and paste it here, and then choose a name for my project. I'm gonna call it pipe flow. Now, next step, I need to create the geometry. So if you remember from module 1, the flow of computation will remain exactly the same. So we start with creating the geometry, we generate the mesh, we set up the model, and then we will be looking at the results. So right clicking on geometry, and I'll start the design modeler. So now once I am in the design modeler environment, and as I said, I would like to work with the 2D axisymmetric condition. So I click on z-axis, so a 2D environment is created for me. And then I go to sketching, I do some changes, I activate the 2D grid and the snap, and I define major grid space to be zero point 0.1. These are just conventions. You can change them to anything that you want. So now I am ready to start my sketch. So I will create a, a rectangle starting from the center of coordinate. Note that when you're working on an axisymmetric geometry, the x-axis should always be the axis of symmetric, this axisymmetric axis that you're considering. So it is important to note that. Now I can assign some dimensions. As we said, the length of this tube is considered to be 3 meters. I keep that. And also the diameter is chosen to be uh, zero point 0.2 meters. But here, since I'm only working on the axisymmetric cross section, I should include the radius here. So instead of zero point 0.2, I'm gonna put 0.1 here. So if you go here, remember the diameter was 0 0.2, but diameter is from here to here. I'm simulating this orange area, which is 3 meter long, and the this length would be 0.1. Okay, now that I have it, I can go to concept, surface from sketch. I I only have one, so I apply and then create generate. It will create a 2D surface for me. So I'm done with the geometry. I save the project. Then I can simply close my modeler. So the next step, as you know, is generating the mesh. So I'm clicking on the mesh generator. So the geometry will be automatically imported here in the mesher for me. It's a 2D configuration. I click on Z to give me the 2D view. If I click on generate mesh, it's going to generate a non-controlled mesh, which is, as you see, is not even acceptable. So I have to adjust and tweak the mesh control. So I right click on the mesh and I insert a mapped meshing. What mapped meshing is doing is telling you that is telling the software that my geometry allows for a mapped meshing. I would like to have the nodes of one side mapped to the node of the other side, and so on. Now again, I will click on the mesh and go to insert. Now I give some sizing. For sizing, I choose this surface, this line, and then this line. I click on apply. I will not assign element size. I would like to work with number of divisions on that line, and I'm considering 100 grid points along the x-axis. So I'm having 100 grid points. Now I change the behavior from soft to hard, and since the inlet and outlet of the pipe need more nodes because there will be gradients of different parameters, including velocity. So I'm going to give it a bias. So I bias this to define a bias factor of, let's say, 50. Okay. Now, again, I need to control this side and left side and right side of this model. So I right click on mesh, go to insert, again sizing, and I make sure the edge selector is chosen. Now I can select this node and then click apply. I would like to assign number of divisions. I'm considering 50 divisions with a hard behavior, and the bias will have to be in a way that the nodes are clustered to the upper side of this geometry, because remember that the x-axis here is the axis of symmetric, which is the center line of the pipe, but up here I have the wall of the tube. Therefore I assign the bias and I give it a bias factor of 50 again. I will have to do exactly the same thing for the other side. So I zoom in here first. I right click on mesh, insert sizing. I select this edge, click apply, element size. I don't want element size. I assign number of divisions, which is 50. Behavior is going to be hard. The bias is required to compensate for high gradients that are available. So note that this configuration of the clustering is not desired. I want the nodes being clustered up here. So I'm gonna reverse the bias, click here, choose this line, and again apply. It will reverse the clustering. Now, if I generate mesh, if I click on generate mesh, and then in order to see it, I can click on mesh, and zooming in shows that a nicely formatted mesh is generated all over the solution domain. Okay, now let's save our model again. So I'm going to save the project, and we're ready to move on to the solver. So if you see this sign, which looks like a spark, it is just telling you that you need to update the project. So right click on the mesh and click update. It'll take a moment to export the mesh from the mesh generator to the solver. Now, once you see this sign, which is like a recycling sign, it is telling you that the mesh has been transferred to the solver and we're ready to set up the model. So I'm clicking on the setup. I want to do a double precision simulation, and as we said, parallel processing is available if we have more than one computational node. If I just click OK, only one computational node of the computer will be used, but I know that my computer has 8, so I'm gonna assign 8 processes here, and then click OK. Once I click OK, the ANSYS will execute Fluent package for me and give me a snapshot of the mesh that is shown here. Okay, now the first thing we need to do is going through the steps. First, we can check to make sure the solver, the Fluent software, is okay with the imported mesh. Once you see a done after checking mesh, it's a good sign telling us that the mesh is okay. We can do a report quality. In these simple problems, usually there is nothing needed to be done. We do a pressure based most of the time, and the velocity formulation is always absolute. Something that we need to change is the 2D space. So previously in 2D problems, we chose a planar configuration, but we know that this is not a planar geometry. This is actually an axisymmetric condition. Okay, something that we did not do was choosing the correct names for each of these lines. So what I'm going to do, I can simply close this solver and rerun the mesh generator. I'm doing this intentionally so that you know you can always go back and forth without losing anything there. So you cannot you do not have to do everything in series. You can always go back and forth. So I want to give specific names. For example, I want this to be my inlet. So I choose it, I choose the line, go to create named selection and call it inlet. The bottom surface, the bottom line here is my axis. So I right click on it, I click on it, then right click, create name selection, I call it axis, then click OK. The right side here is going to be my outlet or exit. So I name selection, click on name selection and write outlet as a name for it. And up here is in fact the wall. So I click on it, right click, create name selection, and call it wall, or you can call it tube wall, and then OK. Now I can simply close this. Once I've done, then see this sign reappears here, which means I need to right click here and click update. Workbench will again retransfer the mesh with the changes that I did to the solver. And then when I see the check mark and this recycling sign, it means that the solver is ready for me. So I'm gonna right click on it again. Now it's telling me that the upstream mesh of this cell has changed. Do you want to load the new mesh? This is because we went back to the mesh generator and modified things. So I'm gonna click yes. Again, my Fluent launcher, nothing changes here. Click on OK. Now I'm ready to proceed. So clicking on model, this time I'm going to turn on the energy equation because I'm solving for heat transfer as well as flow. So I click on model, then on energy, this window opens, which I click on energy equation. It will turn on the energy equation, an additional equation that the solver will solve. My flow is still laminar. I made sure that Reynolds number is in the laminar regime, so I'm not going to worry about that. Materials, as I said, we were going to work with a new material. So in order to create that, I can click on create. It opens this window. I give it a name. I give it fluid X. It's a fluid. And then I can simply change the property. So I know that the density is 1, heat capacity is 1000, thermal conductivity of this fluid X is 2, and the dynamic viscosity is 0.002. And then I click change create. It's going to tell me change or create mixture and override air. I don't want to override air. I just click on no. And then I'm ready to close this. As you see, we have added a new fluid here. So fluid X has been added and we still have air. So now I come to the cell zone condition. Cell zone conditions is essentially whatever you see inside the solution domain, anything but the boundaries. We have to make sure the correct fluid is chosen. So I click on it, this window pops up, tells me the material name. It's by default air, but I want to choose fluid X. That's why I choose it and close it. Next step is defining boundary condition for this problem. So there is nothing we should do for axis. Axis is by default chosen as an axis type. So the Fluent is smart. It knows that when I choose a named selection of axis, that line, that bottom line of the geometry is actually an axis of this axisymmetric condition. So for the inlet, I click on inlet, double click on inlet, then I can assign momentum specification and thermal specification. Previously, we'd never dealt with thermal conditions because we did not solve energy equation. So for momentum, I want to give it a velocity number, average velocity. So the velocity magnitude is 1 meters per second, and I consider it to be normal to the boundary, normal to this boundary, 1 meter per second. And the temperature of air of the fluid entering is 300 degree Kelvin, which we know by default it is actually 300. You can change it here if you want. So clicking on OK. Nothing is needed here. For interior outlet, click on it. We know it's atmospheric condition at the outlet, so right here it is actually an atmospheric condition. Atmospheric condition means the gauge pressure is 0, so I leave it as is. Thermal condition, you see that it is we can change the backflow total temperature, which means that if the situation is in a way that the flow is sucked back to the solution domain, then you can assign a value of temperature for that. But in this case, we know it's not going to happen, so we're not going to worry about it. All right, so the wall, which is the top boundary, it's a stationary wall, no slip condition. So shear condition is no slip, and it's stationary. For thermal, though, I need to make sure I model this heat flux. So I have a constant heat flux of 250 watts per meter squared here. I need to model that. In order to do it, I click heat flux. I put 250 here. I could do different things like thermal. If I knew the temperature of this boundary, I could simply click on temperature and assign a temperature value. If I know a convection situation in which I know a convection coefficient and a free stream temperature, I could work with those. So there are multiple options for a wall situation. In this case, we only want to do heat flux of 250 watts per meter squared. So we click on OK. No dynamic mesh. We don't change the reference values. I go on to the solution. So the methods we're going to use, make sure simple is chosen for a scheme. Everything is second order, so that's good. Go to controls. We don't need to change these. If for any circumstance you need to turn off any equation, you can always click on this equation and turn off these and click OK, but we don't want to do that. We want to solve all the equations. Now, something we need to make sure is that the residuals are small enough. So I make, by default, the convergence criteria for fluent is 10 to the negative 3, but I'm gonna increase this to 10 to the negative 6 for x velocity, continuity equation, x velocity, and y velocity. The energy equation by default has an convergence criteria of 10 to the negative 6, so I'm not going to worry about that. So I can click OK. We're almost ready to initiate this simulation. Then I have to initialize, which, as we know, is giving the software an initial guess to start the iterative solving of the governing equations. These values should not affect your final result. It may change the convergence behavior. It may delay or expedite the convergence, but in general, they should not really affect the results you're getting. So I'm just going to go with the default and click on initialize. Once I do that, I can start the computation by giving the software a high number of iterations. I know that it's not going to do all that because the solution will converge eventually. So I click on calculate and let the software solve the governing equations iteratively. Depending on your computational resource and number of nodes, this may take very long, or it can be very quick. So give it a second to converge. So all the residuals are dropping. You can monitor the numerical values here, or you can look at the residuals of all 4 equations that are being solved simultaneously on this plot. So once the solution is converged, it's telling me that the calculation is complete. If you note here, all these residuals are now smaller than 10 to the minus 6. The most problematic one was this guy, which was the x velocity equation. So now my solution is actually available. I can take a look at it. So how do I do that? So let's start with some qualitative analysis. I want to know if my simulations are make sense. They're right. So I click on contour. I want to see how does the contour of velocity look like. So I click on velocity and click on field and push this. So does this make sense? Yes, it does, because initially everything is at same velocity, inlet velocity. There is a boundary layer formed here. It's being formed, and then as you move along the tube towards the end, then you'll see that the velocity profile is not going to change. It's 0 on the tube wall, and it's the maximum value on the axis. So this is a good sign. If I want to look at, let's say, temperature, I can right click here, contours of temperature, and right click on and click on display. Now again, I'm looking at a flow which is initially at 300 degree Kelvin. A heat flux is added from the top, and as I move along the tube, of course, some heat is being transferred, and my temperature here is going to be more than the temperature here. So to some degree this makes sense, at least qualitatively it makes sense. For example, I can click on vector plot. I can take a look at the vector plot here. I can scale this so I can get a better idea of what is happening. So this is what I expect, right? I expect 0 velocity here, a maximum velocity here, and parabolic behavior. And all we see is only um, qualitative. The quantitative analysis is yet to be done. Okay. Now, one thing we can easily check here is to make sure the amount of mass that is entering the solution domain at the inlet equals the amount of mass that is exiting the solution domain here. So what I can do, I can go here to report and click on flux, and on the flux reports I see that on the options I have mass flow rate. I click inlet, hit control, push, click on outlet, and click on compute. And on the result side, as you see, the total mass flow rate at the inlet and at the outlet are shown. The negative value is telling you that the mass is leaving this solution domain. And the numbers do match. There is a very, very small net result, which is these two numbers are not exactly the same. There is a difference of 10 to the negative 11, which is safely okay. We can agree that these two values are the same. So same amount of mass enters here. The same amount of mass that enters here is going to leave the exit. This is an important thing to note. In some situations, you may see that due to bad mesh or inaccurate results or non-converging situation, these two numbers may not agree. So it is always a good idea to check that. Okay. Um, what else can we do? We can also can look at the path lines. Um, Starting from inlet, the path lines are of course straight lines. We don't really get much interesting things here. Um, we can also plot interesting things. So let's plot the axial velocity right here on the exit. So I go on to the plot here. I click on XY plots, and I choose. So the plot is happening along a y direction. So I choose the direction for x0, change 0 to 1 for y. I want to look at velocity. I want to see the axial velocity. And where do I want to see that? I want to see it on the outlet. So I click plot. And we can see the XY plot, which x-axis is now the radial direction. So radial direction 0 is actually at the center line, has the maximum velocity. Point 1 is telling me that it is at the tube wall and we expect the velocity to be 0, and it is actually 0. So we can in fact try to compare this with analytical solution. So I'm going to save this plot in the form of an Excel sheet, which I can work with easily outside of ANSYS Fluent. So I'm going to click on Write to File here and click on Write. It is going to ask me where do you want to save this data file. You can give it any address or just call it something. So I call it velocity profile and click OK. Then what I can do, I can go to the place that I know the file is going to be. If you don't assign anything by default, it will be under DPFF Fluent Velocity Profile. So it's a data file. The best way to look at these files is to open an Excel spreadsheet and then try opening that. So let me copy the address, paste it here, then velocity profile. Okay, it's gonna tell me that the format is weird. Do you want to open it? Yes, I want. I changed the description of the data from delimited to fixed length. Oh, I'm sorry, it should be kept at delimited. I click on next, and I know there is a space between the files, so I click on space and then click finish. So now let's see what I have. I have been given an XY plot in the form of a table. So 0 is y equals 0, right at the center line, and here y equals 0.1, right at tube wall velocity 0. So I'm gonna copy all these, select it, copy it, and transfer it to another file that I have been creating for this. I paste it right here, and by default I have created this XY plot based on the values that I pasted here. You can simply do it yourself. Now I want to compare this with some analytical solution. So as we know, the velocity profile in a fully developed flow is available. So the solution from from solving the governing equations analytically is available, and it is given here for you for simplicity. The only unknown that we have here is r, and r is the distance from the center line, which is this line, this column. So I'm going to create an equation here for analytical solution. So equals, I'm actually finding u from this equation, so it will be 2 times what was the if I go here, was 1 meters per second, so times 1 times parenthesis 1 minus another parenthesis. R for each point is variable, so I'm gonna click on this, divided by R naught is the radius of the pipe is 0.1. I know that. This should be raised to the power of 2, then close the parenthesis again, and that's it. So I can redo this for all these distances from the center line by simply double clicking on this, and as you see in the XY plot here, I'm plotting both CFD results and the analytical results, and the match is just perfect. So there is a great agreement between the analytical solution and the CFD solution. So note that the CFD results, I got them from the file that I actually generated using ANSYS Fluent. However, this column is the analytical solution coming from this equation, but the results do agree. Okay, that's one way of verifying that my results are correct. So I'm now more confident that the results that we got was in fact acceptable. Now, next step, I would like to look at Nusselt number. How do I do that? In order to find Nusselt number, we need to find the convective heat transfer coefficient. So I created this spreadsheet so that I can explain it for you. On the left side here, we're looking at the properties of the fluids, thermoconductivity, heat capacity, density, and all that. And I actually made sure that the flow is fully developed. Then on the right side, at two different points, I would like to find the surface temperature of the tube at the pipe exit. It will be basically right here. and I can also find the mean temperature, the mass weighted mean temperature of the fluid, the temperature of the fluid, the average temperature of the fluid at the exit here. And if I find that, I can plug it here. I also know the heat flux. The heat flux is 250 watts per meter square, so I can simply put it here. And I will formulate H as heat flux divided by Ts minus Tm. This will be, at the moment you don't see anything because I haven't filled these, but I will do it very quickly. Once I do this, then Nusselt number will be H times diameter of the pipe, which is given here, H times D divided by the conductivity, thermal conductivity of the fluid, which is 2. Okay, now let's fill these two. How do I find the mean temperature of the fluid at the pipe exit? How do I find that? So I go here, I can go to report, I ask for a surface integral. It tells me what kind of report you want. I click on this menu and I tell the software that I want a mass weighted average. If you don't remember what a mass weighted average is, you can go to your heat transfer book and review that section. So I want to find the mass weighted average of temperature. Where do I need to do it? At the outlet. I click on outlet and click on compute. If I do that, the software is going to tell me that the mass weighted temperature at the exit is this number. So I copy this and bring it to my Excel sheet and paste it here. Now, how do I find the surface temperature? Right here. So the surface temperature, it's a little bit tricky. I have to plot the temperature of the surface and then go and find that. So I go to find an define an XY plot. I plot the temperature along. I want to plot the temperature along the wall, so it will be in the X direction. Clicking on temperature, and where do I want to find it? On the wall. I can click here. It will show it to me graphically here, but I want the actual number, so I click on write to file and ask the software to write it. I give it a name like wall temperature. Then I can go here, right click on the file that's generated, open it with a notepad, because I know it's not a I don't need all these information. I just want to find the temperature at the exit of the tube, surface temperature at the exit, which is at 3 meters. I have this number, right click, copy, then come here to my analysis spreadsheet and paste it here. Now look what happened. Now the Nusselt number that we defined is found to be 4.388, and we know that from analytical solution, the Nusselt number in a fully developed condition with a constant heat flux is in fact 4.36. So this is coming from analytical solution. This is the value I found from our computations. So there's a good agreement between them. Now I want to do the same for the middle of the pipe. So I need to go here first. Let me first show you a contour plot so that we can have a good idea of what is happening. So I want to define a line now right at the center. I define a line there. How do I define a line? I go here on surface, create a line. The middle point will have an x of 1.5. So y is 0 for first point. The second point, same x, y will be 0.1, the radius of this type pipe. So I click on, or maybe just give it another name, middle line, create. Then I close it. So now, for example, I can again plot temperature along the middle line. Oops, I should have changed this from 0 to 1. It's a long radial direction. Okay, now what we wanted to do, we wanted to find surface temperature at the middle and mass average temperature of the fluid. We know the heat flux is 250, so we can keep that. So going to the solver again, I go to report, surface integrals, mass weighted average, not at the outlet this time. I want to do it in the middle line, and I want temperature. So click on compute. Software is going to tell me that the middle line mass weighted average is 307.78. I copy this, paste it right here, and the surface temperature, I already opened this. I already found the variation of temperature along the pipe. So this file was the temperature of the wall from x equals 0 all the way to x equals 3 meters. At the middle point, x equals 1.5. So I just need to find 1.5 and copy the temperature of the wall right there. Copy this and paste it right here. I need to define H as before, so heat flux divided by the difference between these two temperatures minus this, and the Nusselt number is H times d diameter divided by k. So a little bit less accurate, but still acceptable. So as you see, the value of Nusselt number does not change significantly along the pipe, but the values have some error in it. This is because our mesh is not the perfect mesh. So if you look at our mesh, you'll see that we could do a better job, which I'm going to ask you to do it as a homework. Okay, the last thing I want you to think about is what would be the contour plot of pressure in this situation. Before I click on display, I want you to take a moment and think about how the pressure is going to look like along a fully developed tube. So if I click on display, you'll see that the variation will be actually very easy. You have a high pressure region here upstream to 0 gauge pressure basically downstream, and this is what is causing the flow. Okay, this summarizes module 2. I hope you can reproduce all these results and then proceed to assignment.